high school AP Chemistry. This is the final lesson on in the subject of kinetics, which we're covering in 1 week. It's a very rapid pass through this subject. Learn as much as you can, do the best you can, study as hard as you can. It's a challenging subject. It's an AP level subject, and we will study it in the future in the spring, but learn as much, get as much in as you can right now. Okay, so this is kinetic rate mechanisms. So let's talk about collision theory. That's part of kinetics. And essentially, chemical reactions happen because atoms, molecules smash into each other, break apart, and then recombine to form new substances. That's the essence of a chemical reaction. So collision theory states that the rate of a reaction will increase with 1. Increasing the number of collisions of reactant molecules, and 2. Increasing the speed of the reactant molecules. And if you remember back, speed should automatically trigger in your mind temperature. Increasing temperature increases the speed. And increasing number of collisions of reactant molecules, that will happen by increasing the speed, but it will also happen by increasing the concentration, that you have more of them packed together in a tighter area. So, a collision must collide with enough energy to create a reaction. The energy required to cause a chemical reaction is called the activation energy. So the energy needed for the reaction to proceed is called the activation energy, and is the highest point on this diagram. So what you're saying is that the potential energy in the bonds of the reactant compounds, that would be A and B in that graph on the left, it has a certain amount of potential energy. In order to break them apart, you have to put in enough energy to get them to break apart, and that's called the activation energy. Actually, it's the amount of energy that those molecules that you have to put in to get those particles to smash together hard enough to break apart, and that's called the activation energy. And you can think of it as kind of a mountain that it has to climb. You see how the curve goes up, and the difference between the original energy that's in A and B and how much it takes to get them to break apart is called activation energy. An example of that would be when you strike a match. The wood will burn, but you have to give it enough energy to get the fire started when you strike the match. So that would be the activation energy. You get enough energy to get it going, and then once you get it going, it can burn on its own. So you'll see on the reaction on the left, it gets up to the activation energy, the reaction starts, and then as the bonds get put together in the new compounds C and D. We talked about that when you put together chemical bonds, when we talked about bond energies, that means that they're going to give off energy. So the energy is going to go down. And then finally you'll have the compounds C and D put together, and they'll be at some lower energy state where they're very stable. Now that's an example of an exothermic reaction, because you ended up with less energy in the products C and D than you started off with in the reactants A and B. So C and D, the line where it levels off is lower than A and B, where the line on A and B is. So that means energy went out of the reaction, and that's an exothermic reaction. On the right is an example of an endothermic reaction. You start off with A and B at a certain energy level. You have to put the activation energy enough in to get the reaction to take place, to get the atoms and molecules to break apart. And then it comes back down. As you put together the bonds in C and D, they're getting to a lower energy, more stable point, and that they come together, they're at a lower energy, more stable point, so energy comes out. But you'll notice that CD ends up at a higher energy than A and B. Is that possible? Can the products end up with more energy than A and B? In some cases they can. So we always talk about the products wanting to go to a lower energy state. Well, they did. They went to a lower energy state than they were when they were separated, with C and D, and all the atoms that will go into C and D were separated. But you end up with more energy going into the reaction overall than coming out. That is possible, and that's called an endothermic reaction. The heat or energy goes into the reaction. Okay, so the activation energy is that point It's the highest point, so it's the point, it's the difference. The activation energy is the difference between the potential energy of the reactants, what their original energy was, potential energy in their bonds, and how much energy you have to put into them to break them apart. So it's really a difference there. So you can see in both cases, it's the difference between where A and B start and how much energy you have to put in to get them to break apart so that they get over that mountain and could go on downhill to become products. So activation energy is the minimum energy required to allow A and B to break apart. Once A and B have broken, they can go back to A and B. In other words, they can get to the top of that mountain and then they can slip backwards. They could end up falling backwards. Or they can recombine to become products C and D. For both endothermic and exothermic reactions, energy must first be put into the reaction and must reach the activation energy. The broken molecules that exist at the top of the diagram are called the activation complex. So when the atoms and molecules are up at the top of that mountain, they're broken apart at that point. So this reaction, the one on the left, is exothermic because the reaction ends at a lower energy than it began with. C and D are lower than A and B. So energy leaves the reaction. That's a negative delta H, negative change in enthalpy. On the right side, this reaction is endothermic because the reaction ends at a higher energy than it began. So energy enters the reaction. That's a positive delta H. That's a positive change in enthalpy. More energy went in than came out. Okay, as temperature increases, rate constant increases. So what this graph is showing you, we said that rate constant kind of is a representation of temperature in a kinetic rate law, but you don't actually put the T for temperature in the rate law, but you use K, and K represents the temperature. So as temperature increases, as you go from left to right on the bottom axis there, the rate constant gets bigger and bigger. So higher temperature means the molecules are moving faster, they're smashing into each other harder, and so the rate constant is going to go up. That means the reaction is going to happen faster. What the curve means is this. It means as you first start to increase the temperature from maybe a kind of a moderate temperature and get it a little bit warmer, then the rate constant goes up a little bit. You can see it. It's kind of a flatter end of the curve. But as you really start to increase to higher temperatures, the rate constant really takes off. It gets steeper. So it increases faster as the temperature is higher. So when you changes in higher temperature will cause the rate constant to change a lot more than changes at lower temperature. So that's what that's simply saying. Okay, the curves below are called a Maxwell-Boltzmann distribution. The area under the curves is the same for all four curves. The red dashed line represents the activation energy, the minimum energy required for the reaction to take place. Higher temperature means higher molecular speed. So kind of take a look at this. The turquoise line, the one at 100 K, that's the one that's at the lowest temperature of those four curves. And you look at it, and every part of that curve, 100% of it, is to the left of that red dashed line. You have to cross that red dashed line in order to have enough energy for the particles to split apart, to break apart. That's the activation energy. So you'll notice that none of the particles, no part of that turquoise curve is to the right of the red dashed line. That means none of those atoms or molecules in that set would have enough energy to break apart. They just don't have enough energy. If you look at 300 K, you have a small fraction of them that are to the right of the dashed red line. That means a few of them will break apart, but not very many. 600 K, that's more. And 1000 K, it looks like roughly half of them have enough energy to break apart and half of them don't. So that's what a Maxwell-Boltzmann curve tells you. You don't need to memorize, the name Maxwell-Boltzmann distribution. Just understand when you see one, what does it mean? So the activation energy on the graph is 1,000 meters per second. None of the molecules under the turquoise curve have enough energy to react. About half of the molecules under the red curve have enough energy to react, to break apart. The Arrhenius equation relates temperature, activation energy, and the rate constant. The Arrhenius equation is this, okay? Looks kind of messy. And what it is, though, when you look at an equation like this, what you really want to understand is what are the things that go into making the rate constant? So this will tell you what the rate constant is a function of, what things contribute to it, and therefore things that are not in this equation don't contribute to it. For example, pressure has nothing to do with the rate constant. So when you read an equation like this, you want to try to sift out what is it telling me about what goes into making the rate constant. Again, the higher the rate constant, the faster the reaction goes. So let's read this. A. What is A? A is called the frequency factor, and it takes into account the orientation of the molecules. Orientation is important because molecules must strike each other at the proper direction. So it's the direction that they're pointed. The example I give in class when we're in class is I take a wooden stick, just a nice kind of light wooden stick, and I smash the end of it against the corner of a table, and I say, I can't break it. Why can't I break it? Because I'm trying to hit the end of the stick against the table, against the corner of the table. But if I turn the stick sideways, so lengthwise, and hold it and hit it against the side of the table, it'll snap very easily. So that's what orientation means. It means in what direction are the molecules facing. If they're not facing in the proper direction, they won't break apart. So that's called orientation. EA is the activation energy, the amount of energy a molecule or compound must have to react. EA is the energy mountain. It's that high point that we saw in those curves back there, and that molecules must climb in order to react. So that's called, you saw what activation energy was. T is the temperature in Kelvin. R is the gas constant, but it's not the 0.0821 liter atmosphere over moles Kelvin that we use with PV equals nRT. It's a different one, and I could show you how you derive the J equals mole over Kelvin from liter atmosphere over mole Kelvin, but it's not worth the time. Just to understand, it's just a different way to represent the gas constant. You're using joules in the numerator, that's the unit of measure for energy, instead of liter atmospheres that you have in the traditional one that we use with PV equals nRT. So be sure you're going to have problems where you have to be sure you use the proper gas constant, and you just learn from experience which one it's going to be. And then E, of course, is Euler's number. That's the E that we've been talking about when we've been talking about natural logs. All right, so that describes. So what you want to come away with is, what does the rate constant, what is it a function of? It's a function of the orientation and the frequency that the molecules hit each other. That's A. It's a function of the temperature. That's T. And it's a function of how high the activation energy is. So the Arrhenius equation relates temperature, activation energy, the frequency factor to the rate constant K. The Arrhenius equation, there it is again. And the way you have to interpret this is, when you see this factor, negative EA over RT, that's in the exponent of E. As E becomes greater, then that exponent becomes more negative. Notice, because it has a negative sign. That means that the term E, that E term, is going to become smaller and smaller. So in other words, as you have a higher activation energy, then that means that it's going to be harder for the reaction to take place, so the rate constant is going to get lower and lower. K is going to get lower and lower. So let's read this. What is the relationship between the exponent EA, negative EA over RT and K? So first, as the activation energy EA gets higher, the term negative EA over RT becomes more negative. So K decreases. That means the reaction becomes slower. High activation energy means it's harder for the reactants to get over that mountain, that energy mountain that we saw in the earlier graphs. So this happens because a particle requires higher energy to react. Fewer particles have this amount of energy, so the reaction slows down. Okay, what is the relationship between the exponent negative EA over RT and K? So let's look at temperature now. So 2, at the temperature T gets higher, the term negative EA over RT becomes less negative. Okay, I know it seems weird because it's in the denominator, and you think as that gets bigger, it's going to make the overall fraction smaller. It is. It's going to make EA over RT smaller, but remember, it's a negative, and a negative exponent makes something smaller. So you kind of got to get your mind wrapped around that. As EA over RT becomes smaller and smaller, then that negative overall, with the negative sign there, it doesn't decrease K as much. So K increases the faster reaction. The really only way to see it is by plugging in some numbers. This happens because higher temperature puts more energy into the particles, so more particles reach activation energy and speed up the reaction. That's all you have to realize, and this is common sense. Increasing temperature is going to make the reaction happen faster, so K is going to increase when you increase temperature. Okay, finally, let's look at A. The term A is called the frequency factor. This takes into account the frequency with which the particles collide, and that is somewhat a function of temperature, but it can be a function of other things as well, like the number of moles. The frequency with which the particles collide and the orientation. Are they pointed in the right direction? Now you may ask, how can they measure the orientation? How do you put a number to that? And the answer is, I don't know. But none of your chemistry book, your textbook won't explain it either. It's just something that they come up with through experiments as to whether the A is a bigger number or a smaller number. Only particles that are oriented pointed in the right direction will break apart. So you can clearly see as A gets bigger, K will get bigger. The Arrhenius equation relates temperature, activation energy, and the rate constant, and also the frequency factor, I should add into that. Okay, so what you can do is you can take the natural log of both sides. Here we go again with natural logs. So the Arrhenius equation can be written, I won't do the math, but if you just take the natural log of this, what you end up with is that equation down there. Okay, so just trust me, that's what you would get. You get ln k equals that exponent, negative EA over R times 1 over T plus ln A. And it's been broken up in such a way that it forms the equation for a straight line, y equals mx plus b. So the independent variable is 1 over temperature, that's the x in that equation, and the dependent variable y is the natural log of k. The natural log of A is going to end up as the y-intercept in that equation. So why do we use natural logs ln? To create a straight line of the data. Okay, so what's the slope in this? Well, it says at the bottom, the slope is negative EA over R, because that's the coefficient in front of 1 over T, which is your variable x. That's the slope. M is the slope. Okay, again, don't worry about deriving the math. Just kind of learn the equation, and the equation can be written down on a piece of paper. We can calculate K at a certain temperature if we know K at another temperature. So again, there's more math that I'm not going to show you here, but you can take the K for a certain temperature T, let's call this T in this equation here T1, write the equation a second time for a different temperature T2, and then that means you have a K1, this would be K1, and then you write the equation a second time for K2. And when you put those together, again, so earlier we said, let me just read this. Earlier we said that the rate constant K is a function of temperature. Remember the glow sticks. You guys didn't get the glow sticks, okay? Because we're not in school. You would have gotten to see glow sticks. But what happens with glow sticks? They become brighter in warm water because the reaction happens faster. We can apply this equation twice to the same straight line to find different rate constants at different temperatures. Again, we will not show the math, so here's the equation. Here it goes. There it is. It's the natural log of K2 over K1 equals negative, that slope that we just said that was a slope, EA over R, and then it's times the difference in temperature, or the reciprocal of the difference in temperature. Again, don't worry about how they got the math on this. It's just basically taking that equation up there, making it a second time, and putting it together. So we know that K changes with temperature. This equation gives us a way to take the known rate constant K for a particular known temperature and figure out the rate constant at a different temperature. So in other words, we know the rate constant at a certain temperature, and we want to know what it is at a different temperature. We can figure that out using this equation. So the activation energy for the following first order reaction is 102 kilojoules per mole. The value of the rate constant K is 1.35 times 10 to the negative fourth, at 35 degrees centigrade. You have to convert that to Kelvin, so that's 308 Kelvin. What is the value of K at 0 degrees centigrade, which would be 273 Kelvin? So in other words, we know the rate constant at 35. We want to know what the rate constant would be at 0. So think about it. Would the rate constant at 0 be a bigger number or a smaller number than at 35? Think about that. Well, it would be a smaller number because 0 degrees is less than 35. So there's going to be a lower temperature, means the molecules aren't going to move as quickly, and therefore the reaction is going to go slower. So we'll actually just plug some numbers in. Even though it looks like kind of an intimidating equation, it's really just plugging in numbers and being sure you don't make a math mistake. So the activation energy is measured in kilojoules per mole. You see it up there at the top, 102 kilojoules per mole. This can be converted from kilojoules to joules because the gas constant is measured in joules. So you've got to convert from kilojoules to joules. So 102 kilojoules is 102,000 joules per mole. And the gas constant we have to use is the 8.31. There's two gas constants. The one we use with PV equals nRT is 0.0821 liter atmospheres per moles Kelvin. You can't use that one. Why? Because it doesn't have joules in it. So you have to do the conversion to use this one with joules, and it's 8.31 joules per moles Kelvin. It's the same gas constant, it's just expressed in different units. Okay, so the value of the rate constant, there's all the data again. And we remember that we had 102,000 joules to work with. Okay, so there's all the data over there. There's the variables. So you're trying to find K2. What is that rate constant going to be at 0 degrees at T2, 0 degrees centigrade? So you have all the other data over there. So now it's just plugging in the numbers, and there it is. You want to be sure you plug things in properly. If you're into doing the unit cancellation here, you see that joules on the top, numerator top and denominator top cancel out. Moles in the numerator bottom and denominator bottom cancel out. So you're left just with Kelvin, but that Kelvin in the denominator bottom flips up to the top. It goes up to the top. And then you have the Kelvins in the denominator of the 273 inside the parentheses. Anyway, what you're gonna end up with, you'll end up with the proper units of measure. Okay, I won't go too much farther than that, but if you want to do the unit cancellation, you can. I'm not going to. All right, there we go. So we have that ln over on the left-hand side, right? So how do we get something out of a natural log? We use the inverse property. We raise e to that exponent, and it looks like a big exponent, and it is, but that's okay. And then everything, once you simplify the right-hand side of that equation, the 102,000 over 8.31 times 1 over 273 minus 1 over 308, once you simplify that, you would end up with negative 5.1. So you raise e to the power of both of those sides. So that means the K2 over 1.35 and all that comes out, and you totally reverse. You inverse the e in the natural log. And then you take e to the negative 5.1 over on the right, and that gives you 0.00606. And now it's just algebra. You do that, and you end up with 8.18 times 10 to the negative 7. Don't worry about the unit of seconds to the minus 1. It means 1 over seconds. Don't worry about it. So what does that mean? Let's go over here to the bottom left. K2 is 8.18 times 10 to the minus 7th, which is less than K1, which is 1.35 times 10 to the minus 4th. In other words, K1 is about 1,000 times bigger than K2 because the exponent is less negative. That happens because the reaction runs slower at 0 degrees centigrade than it did at 35 degrees centigrade. Okay, messy equation. It's just arithmetic. It's just knowing how to manipulate that equation and plug in the numbers properly. Okay, a rate mechanism. So we're no longer in Arrhenius equation as it says on the top. We're dealing with something called a rate mechanism. A rate mechanism is the series of steps that a reaction follows to get from reactants to products. So far in a chemical reaction, we've always just talked about it like it's magic. You have a bunch of reactants, and all of a sudden, abracadabra, they turn into a bunch of products. But they don't really. They have to do it in a series of steps. Think about when you're baking a cake. You have a bunch of ingredients that you need for the cake. You have eggs and milk and sugar and flour and and butter and whatever else, and you want to end up with a cake. They don't just magically turn into a cake. You got to do a series of steps, right? With the eggs, you got to do them. You got to put them together. You got to stir it around. You got to do all that. You got to mix everything. You got to put it in the oven. You got to bake it, and finally you come out with your cake. Well, it's the same thing here. A chemical reaction doesn't just happen. It happens in a series of steps. Sometimes it's fairly simple. Sometimes it can be very complicated. In this class, we'll only deal with some pretty simple rate mechanisms. So it's a series of steps that get you from the reactants to the product. So let's go ahead and jump into some examples and we'll see. For example, the reaction 2NO plus O2 gives you 2NO2. You can see that's a balanced reaction. It's a pretty simple reaction. Okay, so that does not happen in one step. So the reaction consists of two steps. In the first step, you have NO and NO molecules smashing together and producing N2O2. Then in the second step, the N2O2 combines with the oxygen and that produces 2NO2. So those are the two steps. It doesn't just happen magically in one step. It takes two steps for that to happen. First, you have to break apart. You have to break apart the NOs, and then they recombine as N2O2. And then you take the N2O2 and the oxygen that you had at the beginning. You smash those together. You break them apart, and they end up as 2NO2, which is the final product in the original reaction up there above. Okay? So NO2 does not appear in the original reaction, but it appears as a product in step 1 and is consumed as a reactant in step 2. That's called an intermediate. So you're actually making a substance in the middle of this reaction that gets produced in step 1, and then it totally gets used up in step 2. You don't see it at the beginning of the reaction, you don't see it at the end of the reaction. That's called an intermediate. Each of the individual steps in the reaction is called an elementary step. Okay, so step 1 and step 2 are called elementary steps, which result in the overall reaction up above. Okay, now we're going to study the rate mechanism for this reaction. So let's say that it has been experimentally determined that the rate law for this reaction is rate equals rate constant K times the concentration of H2O2 times the concentration of I minus. Okay, remember how we did that when we had the table of concentrations of the different reactants and the rates, and you had to isolate them one at a time and figure out what the exponents were and what the K was. So they're saying that that's what they did here, and that's how they figured this out. So H2O2 is first order, the exponent is 1. I minus is first order, exponent is 1. The overall order of this entire reaction is second order because 1 plus 1 equals 2. Go back and review the second lesson if that's all a little foggy for you. But this is going to be a 3-step process. So the rate mechanism has 3 elementary steps. And we're going to write the rate law for each step here. So here we go. So step 1 is, and you, by the way, you don't figure these out. They have to be given to you. So just, take a deep breath and say, oh my gosh, where did this come from? You don't have to know that. It was determined experimentally. All right, so H2O2 plus I minus gives you HOI, hydrogen oxygen iodine, plus hydroxide ion H minus. So what would be the rate law for that? It would be rate equals K1, that's the rate constant for this step, for step 1. It is the concentration of H2O2 times the concentration of I1. Now I'm going to tell you something that I'm going to introduce you to in just a moment. Remember we said that the coefficients in front of the reactants, if for example there had been a 2 in front of the H2O2, that does not become the exponent. We said that for an overall reaction. But for an elementary step, it is true. It does become the exponent. So let's say there was a 2 in front of H2O2. It would become the exponent H2O2 to the second power over there on the right-hand side in the rate law. So let me say that. If I had a 2 right here where I'm circling my cursor, that 2 would go up here as the exponent. Only for an elementary step reaction, not for an overall reaction. We said earlier back in the second lesson, you can't use the coefficients for exponents. They have nothing to do with that. But here you can do it. Don't ask why. You don't need to know why. You just need to understand it when you solve these problems. All right, so there we go. There's the rate law for step 1. Let's do step 2. So what step 2 is saying is that if you take the OH that was produced in step 1, the hydroxide ion, and you mash it together with the hydrogen H plus ion, the hydronium ion it's called, that what you get is water. OH minus plus H plus gives you H2O. You get water out of that. So what's the rate law for that step? Well, it's K2. It has its own rate constant, K2, and then it's OH and concentration times H plus concentration, and there you go. Since the coefficients in front of OH and H are both 1s because you don't write them, that means the exponent above OH minus and H plus is also 1. Again, that's only true when it's an elementary step reaction that you can use the coefficients as exponents. Okay, I'm going to say that 100 times because you want to be sure that sinks in. Finally, the third step in this reaction. You take HOI, which you produced back in step 1. You take some hydrogen. You didn't use all the hydrogen in step 2. You just used some of it, the hydronium, the H+. So you take some that you didn't use in step 2. And then you take some iodine that you didn't use up there in step 1. And you smash those together. And you come out with I2. That's an iodine diatomic molecule. That's the way iodine likes to be. It likes to be a diatomic molecule, I2, plus H2O. So before I make it appear, what's going to be the rate law for that step? Think about it. There it is. It's the rate is going to be K3. It has its own rate constant times the concentration of HOI raised to the first power because the coefficient in front of HOI is 1, times the concentration of H plus to the first power because the coefficient in front of H plus over on the left side is 1, times the concentration of I minus raised to the first power. So now you have 3 elementary steps and the 3 rate laws for each of those. So key point, this is what I was telling you earlier, instead I'm going to say 100 times. For an elementary reaction, you can use the coefficient on the reactants as the exponents in the rate laws. Only for elementary reactions. Remember, we learned earlier in this unit that you must determine exponents for the overall reaction experimentally. And that's what they did up here. There's the overall reaction up here at the top, and there's the overall rate law for that reaction. That had to be done experimentally. Okay, so let's move on. So it has been determined experimentally that the rate law for this reaction is that, what we showed you on the previous slide. So the rate mechanism has 3 elementary steps. There they are. We've already gone through those. So you can see that the rate law, see if you notice something about the rate laws of the elementary steps and the rate law of the overall reaction. Well, you can see that the rate law of the overall reaction is the same as the rate law of step 1. This means that the speed of step 1 is limiting the speed of the reaction. Therefore, step 1 is called the rate determining step. So see, the rate law for step 1 is the same as the overall reaction. In other words, the reaction cannot run any faster than its slowest step. Let's say I had 3 ASB students who were putting together care packages for Hoover students. And in the care package, they're going to put some candy and some pencils and some paper. Okay? And let's say that the person who puts the candy in the package is really fast. And let's say the person that puts the pencils in the package is really fast. But the person who puts the paper in is really slow at putting paper in. So what does that mean about how fast the care packages can be produced? They can only be produced as fast as the slowest person. So they can only be produced as fast as that paper person, the slow guy, can put the paper in. Similarly, when you have a reaction, an overall reaction, it can only run as fast as the slowest elementary step. And in this case, the way you know that, how did you know that step 1 was the slowest? You didn't. But you can identify it because since the rate of the overall reaction is the rate of step 1, that tells you that step 1 is the slowest step. The reaction can't run any faster than its slowest step. And again, the name for that is called the rate determining step. Okay, molecularity. The molecularity of a reaction refers to the number of molecules that participate as reactants. So unimolecular means one reactant only is involved. Bimolecular means that you need two reactant molecules. They can be the same. And terramolecular means that three reactant molecules are involved. So unimolecular example, that would be a decomposition reaction where you have just a single reactant and it comes apart. It decomposes. That would be it. Bimolecular would be 2H2 plus O2 smashes together to give you 2H2O. And terramolecular is really a tough one. You have to have three molecules all hit each other at the same time. Generally you would think of it as being that way. Okay, so here are some examples. So molecularity, unimolecular, you have a single elementary reaction, so A. So therefore the rate of that, since you just have one reactant, it's first order, it would be rate equals K times the concentration of A. For bimolecular, if you have A plus A, that would be like hydrogen plus hydrogen forming a hydrogen molecule. The rate would be concentration of A squared. Bimolecular would be A plus B. That would be two different atoms or molecules combining, and that would be the rate is concentration of A times concentration of B. If you have terramolecular, you have A plus A, and that would be rate equals K, A raised to the third power. And terramolecular A plus B would be A squared B on the concentrations over there on the right. And terramolecular of three different molecules or three different reactants would be A plus B plus C, would give you a rate of A plus B plus C. So you'll notice something here. In the first bimolecular one where you have A plus A, you notice that what you have is you can raise that to the second power. When you have A plus B, then A is first power, B is first power. When you have A plus A, then that's A to the third power. When you have A plus B, you have A to the second power, B to the first power, and A plus B plus C, everything's to the first power. So you'll notice that you can use the coefficients of A if you add them up. So A plus A is 3 A's. So that means your exponent would be 3. That's why in an elementary reaction, the coefficients can be the exponent in the rate law. So note that A plus A is the same as 2A, if we write it like an algebraic expression. If we rewrite the reactions in this format, they appear as follows. Okay, so it's what I was just saying. All right, and you can see that the coefficients are going to be the exponents in the rate law. So that's why you can do this if you're dealing only with elementary reactions. This is true. So you can see that the exponents in the rate laws do equal the coefficients of the reactants. This illustrates the point made earlier that for elementary reactions only, you can use the coefficient on the reactants as the exponents in the rate laws. Compute the rate law for the reaction without using experimental data, but using the rate mechanism shown below for the reaction. So we're going to take this reaction, so it's 2N2O. Well, it's a decomposition reaction, and it will break down into 2N2 plus O2. And that is a balanced reaction if you check it out. So since the first step is slow, and the way you know that is because the heading says mechanisms with slow initial step. So we're going to assume that the first step is slow. Its products, N2 and O2, immediately become reactants for step 2, and the overall reaction is completed. So here's the first step. This is happening very slowly. So N2O is breaking into N2 and O, and that's happening very slowly. The fast step is the next step. Now, what does slow and fast mean? It just means that the slow step is slower than the fast step. There's no specific amount of time we're putting on them. We're just saying that it's slower than the fast step. So what that means is the second step needs to have some N2O. So not all of it was used in this first step. You see N2O is the reactant in the first step. It's also a reactant in the second step. Not all of it is used in the first step. But what the N2O in the second step needs is that oxygen that was a product in the first step, in step 1. So as soon as that oxygen is produced, it's produced so slowly, the second step will gobble it up and put it into the reaction and come out with the products in the second step of N2 plus O2. So again, somebody is putting together our example of putting together booklets. Somebody is assembling the pages, and that person is really slow assembling the pages. And then somebody has to staple them. That person's really fast. So as soon as the person assembling the pages puts them together and hands it to the stapling person, bam, 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 they put the staples in, they put it on. Now the stapling person, who's the fast step, is waiting for the next booklet. And they're waiting and they're waiting and waiting. Finally, the person gets the next set of pages put together for the booklet, hands it over to the stapler, and bam, 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 he staples them and sends it on. So the stapler is gobbling up those booklets, is using is stapling them as quickly as he's getting them, or she's getting them. Okay? So that's what is happening here. As soon as that slow step, number 1, puts out that oxygen, it's immediately taken in by step 2 and combined with the N2O2 to come out with your final products. Okay? So you cancel the O's. And so now we're going to see, do these 2 steps actually give us our overall reaction up above? So we do this just like Hess's law. That's why we canceled the O's. We actually subtracted them because they're on opposite sides of the arrows. Now we can add things on the same sides of the arrows. So we can add N2O plus N2O, because each step 1 and step 2 both have that. That gives you 2 N2O. And then on the right side of the arrow, you see you have N2 and N2 in both reactions. So you add those together to get 2 N2. And then the O2 only exists in the step 2 reaction, so you bring that down, and that's O2. So that is our overall reaction, the one up on the top, as you see. So the rate law for the overall reaction equals the rate law for the slowest step. That would be rate equals K N2O, K times the concentration of N2O. So step 1 is the slow step. It only has one reactant, that's N2O. So the rate law for that step 1 is going to be rate equals K times N2O, concentration of N2O. And that's going to be, if you look up at the overall reaction up on the top, that's going to be the rate law for that reaction. It's going to be K times N2O. Remember, the 2 in front of the N2O up there is not the exponent. All right? Because that's an overall reaction. It's not an elementary reaction. So that's the rule to remember, is that in this type of situation, the rate law for the slow step is going to be the rate law for the overall reaction, because the overall reaction cannot happen any faster than its slowest step. Now we're going to go on to a more complicated case. Okay, so this is a rate mechanism where the second step is the slow step. So the first step is faster than the second step. That's the opposite of the last example. So a rate mechanism with a slow final step creates a small complication shown in this example. Okay, you might want to take a 5-minute break before you do this, because it's going to require a little thinking here. Here we go, but we're almost done. Compute the rate law for the reaction without using experimental data, but using the rate mechanism shown below for the reaction. So there's the overall reaction. It's 2NO plus Br2 will give you 2NOBr. And if you check that out, that is a balanced reaction. So here's step 1. It's NO plus NO gives you N2O2. And we're going to say that's the fast step. Step 2 is the slow step. And it's N2O2 plus Br2 is going to give you your final product in the overall reaction, which is 2NOBr. Okay, so something that you're going to learn more about after Thanksgiving is those double arrows there. What do they mean? Up until now, we've just assumed that reactions all go from reactants on the left over to products on the right, 100%. But double arrows mean they can go in both directions. And what it also means is that you don't end up with all of the reactants, NO, turning into all products, N2O2, in that reaction. It means they find kind of a balance, where when the reaction has pretty much come to a conclusion, you still have some NO left in the pot, and you still have some and you have N2O2 left in the pot. And depending on how much of either of those you have depends on other things like temperature and the concentrations, how much NO you have, how much N2O2 you have. But basically the reaction, you can think of it as kind of stopping in the middle somewhere. It doesn't go all the way to products, and it can go back and forth. It can go from products back to reactants, reactants to products. And that's called an equilibrium reaction. We're going to learn about that in the week after Thanksgiving. Now the second step is the slow step. That's the N2O2 plus the Br2 gives you your final product of the overall reaction up above of 2NO2. So let's think about what's happening. You're taking NO plus NO and you're creating N2O2 really fast. But the second step is kind of slow to take it in. It does take in the N2O2, combines it with Br2 to get 2NOBr. But the first reaction is fast, and the second reaction doesn't take it in as fast as it would like. So what happens to the N2O2? Well, some of it will go down to step 2 and become part of that step 2 reaction, but step 2 is really slow taking it in, so some of it will go back to reactants. It'll go back to NO. So it can go in either direction. It can either, the N2O2 in step 1 can either go down to step 2, or it can go backwards in step 1 to create those reactants, NO and NO. So that makes the situation a little bit more complicated. So we're going to go ahead and write the rate laws for each of these elementary reactions. First we're going to go ahead and add them, and we'll see that this reaction does work. So you're going to cancel out the N2O2 on either side of the arrows, and now we're going to use Hess's law. So what we have is NO plus NO up above, and that gives us 2NO, just like algebra. And Br2 comes down, that's Br2. And then the final reactant of the overall reaction is there at the end of step 2. That's 2NOBr, and there it is. So you can see that these two reactions do give us our overall reaction up above. But doing the rate law is a little bit more complicated, so let's see how that works. So the rate law for the overall reaction equals the rate law for the slow step. And the slow step in this case is step 2. So what is the rate law of step 2? Well, let's look at it. It has N2O2. This is before we canceled it to add them. It has N2O2 and it has Br2. So it's going to be, rate law is going to be K N2O2 with an exponent of 1 because the coefficient in front of N2O2 is 1, times the concentration of Br2 also with an exponent of 1 because the coefficient in front of Br2 is 1. So again, we're looking at step 2, the slow step. So that's the rate law, but here's the problem. Look at that rate law. It has N2O2 in it. Look at the overall reaction up above. There's no N2O2 in that overall reaction. So that can't possibly be the rate law for the overall reaction. The overall reaction has to only have NO and Br2 in its rate law. So this seems to violate our rule that the slow step rate law is going to be the rate law for the overall reaction. Well, it doesn't. It's just we have to do some chemistry math manipulation to get it to do that. In other words, N2O2 is what we called an intermediate. It's produced in the first step, and it's totally used up in the second step. So it doesn't exist in the overall reaction. It doesn't exist up there in the overall reaction. So it cannot be in our rate law for the overall reaction. The only things that can be in the rate law for the overall reaction are NO and Br, the two molecules that you see up there in overall reaction. So how do we solve that problem? Okay, so here we go. Pay attention, and you might even want to listen to this a few times. Okay. So, but there's a problem. The temporary rate law includes an intermediate N2O2. The final rate law should only include the reactants in the final equation, NO and Br2. For this reason, we need to find a way to express N2O2 in terms of NO and Br2. We have to get rid of that N2O2. So here's how we do it. So we got to take step 1 here, And what you notice is it's a reversible reaction. It goes in both directions. So we're going to write it as two separate reactions. One that's going forward from left to right, which is the way we're normally used to thinking of it. And then we're going to take it and flip it around and write it in the other direction. So this is a reversible reaction, which means it can go both ways. So it can be written with two different rate laws, one for the forward and one for the reverse reactions. So watch how we do that. So the forward reaction is just what you would think it is. It's NO plus NO gives you N2O2, and it's only going from left to right. Now the rate law for that would be rate equals K, rate constant, F. That stands for rate constant for the forward reaction. And since you have NO plus NO, it's going to be the concentration of NO squared. That makes it a second order reaction. Okay, a second order rate law. Okay, now let's do it in the other direction. We just flip the equation around, so the N2O2 is on the left and the NO are on the right. So the way you would write that is the rate is K reverse. That subscript is a little r for reverse, in the reverse direction. And that's simply going to equal the only reactant, the concentration of the only reactant you have in this reaction, which is N2O2. So you have two different rate laws for the forward and reverse. So one thing you need to understand about a reversible reaction, an equilibrium reaction, is it's not just standing still. Reactants are turning into products and products are turning into reactants. But at equilibrium, those two things are happening at the same rate. Okay, if we were in school and I had 30 students in my class and the teacher next to me, Mr. Andrews, had 20 students, we'd have an equilibrium. We'd say he's got his 20, I got 30. Okay. Now, if 5 students go from my class to his class, and then 5 different students come from his class back to my class, then I'm still at 30 and he's still at 20. If 2 students come from his class over to my class, and then I send 2 different students over to his class, then we're still at 30-20. So that's an equilibrium. We're keeping our 30-20 classroom sizes, but it's called a dynamic equilibrium because the students are going back and forth. They're not just staying in one classroom, they're going back and forth. The same thing is happening here. Products are turning into reactants, and reactants are going backwards and turning into products, but they're doing it at exactly the same rate at the same time. That's why it stays in equilibrium. And so these two rate expressions over here have got to be equal to each other. They've got to be moving at the same rate forwards and backwards. So the reaction which will reach an equilibrium, which means that the forward and backward reactions will happen at the same rate, and we can equate the two rates. So watch what we do. We would simply do that the K forward, the rate constant of the forward, times the reactant of the forward reaction, which is NO squared, equals the rate constant of the reverse reaction times the concentration of the reactant of the reverse reaction, which is the N2O2. So just stop for a second, pause the video, look at this, and be sure you're comfortable with what's going on there, okay? They have to be going back and forth at the same rate, so you set them equal to each other. Now what we can do is do a little algebra. We can solve for N2O2. And we do that by dividing both sides by Kr. So if you divide both sides by Kr, over there on the right you see that N2O2 concentration equals Kf over Kr times NO squared. Alright, so now we've taken this N2O2, which we're not allowed to have in our final rate law, and we've expressed it in terms of something that we can have in our final rate law, which is the NO. So it's Kf over Kr. Now you say, what are those? Well, it doesn't matter. You're going to see in a second. Times the concentration of NO squared. Okay, so we can substitute N2O2 equals Kf over Kr NO squared, what we just figured out, into the temporary rate law for the complete reaction. Okay, so there is the temporary rate law, and now we know that N2O2 equals Kf over Kr NO squared. So to get the rate law, we do this. We take that N2O2 and take it out and put in Kf over Kr NO squared. So now what we have is a rate law that doesn't have the intermediate N2O2. That was prohibited. We weren't allowed to have that in our final rate law. And we do have a rate law that's in terms of only the two molecules, compounds, reactants that were in the overall reaction, which is NO and Br2. Now what do you do with all those Ks? You just lump them together, and they're constants. They're not going to change. So you just put them all together into a single K, which is the overall rate constant for the overall reaction. So you just do this. The three rate constants, KT, that's K temporary, KF, that's K forward, and KR, K reverse, are all constants, so they combine to form the final rate constant K. The final rate law includes the reactants for the overall reaction, and there it is. So if you go back to the original reaction, it only had NO and Br2 in it, and so now you have a rate law for the original reaction. I would recommend you watch these last 10-15 minutes when I explain this several times. You're going to work some problems with this, and once you work a few problems, it will make sense to you. Okay, one last concept is catalysts. A catalyst speeds up a chemical reaction without being part of the reaction. A homogeneous catalyst exists in the same phase as the reactants. That's liquid-liquid, solid-solid, gas-gas. For a catalyst to work, it must do at least one of the following: increase the number of collisions of reactant molecules, or lower the activation energy for the reaction AE. So it can do either one of those things. If you took biology, a biological catalyst is called an enzyme. Enzymes are specific to biology, but catalyst in general means it could be any type of chemistry. It's something that speeds up a reaction. The reaction pathway shows the activation energy, the highest point on the curve, is lowered in the presence of a catalyst. The beginning and ending energy levels are not changed. So what would happen if we were doing one of those elementary mechanisms that we were just doing with slow steps and fast steps? If you have a catalyst, it appears at the beginning of the first step, and it appears at the end of the last step. In other words, it does not get consumed or changed by the reaction. It just has a way, we don't have to get into the details of it, of speeding up the reaction. But it does not become a part of the reaction. So again, it would be at the beginning of the first step and the end of the last step. And when we do work some of the problems, you're going to see that. Okay? All right, that's it. If that made your head hurt, here's the good news. We're done with kinetics, but you're really not done with it. You need to study this. It's about 85 or 86 slides that I went through in 3 videos. Watch them a second time, watch them a third time. There's a long problem set to go with this, and I'm going to get that up by Wednesday morning, and you're going to have basically 5 days to work on that. You should plan to work on this over the weekend. It is a lot, and I got to just say, guys, this is a challenging subject, and it's going to take some serious effort on your part. Okay, you're capable of doing that. I believe in you, and I would just come to me for help more often if you have issues with this. Don't just give up on it quickly. Don't give up on it at all. All right, so that's it. I'm going to get the assignments up for this, and you will have those to work on for the rest of the week and weekend. All right, so have a good day. I'll see you in class on Friday.